So can I begin? Is everything fine?
Yep, please take it away.
Okay, great. So, okay, just a brief outline before I start the presentation. So first, I will just give a very brief overview of the direct two-point energy measurement protocol, the TPM protocol, just in case anyone is not familiar with it. And then I will describe how you can include the description of the measurement apparatus used in the TPM protocol. And then I will motivate and explain what I mean by self-consistency of the TPM protocol performed on both the system to be measured and the measurement apparatus. And I will say when, like, the sufficient conditions which will allow us to have satisfy the unmeasured first law of thermodynamics for all for the total work for all system states and system-only unitary processes. And finally, I will describe the necessary and sufficient conditions for the total work distribution to be equal to the system-only work distribution, again, for all system states and system-only unitary processes. So what is the unmeasured work for a thermally isolated system? So consider a device seen as a black box where a system initially prepared in a arbitrary state rho enters the device and undergoes a unitary evolution V, thereby exiting this device. Now, so this system, before and after it enters the device, has a constant bare Hamiltonian H, but it is mechanically manipulated by a time-dependent Hamiltonian, captured by this interaction term HIT, which generates, which is non-vanishing only for times after the system enters the device, so times, so it's vanishing before it enters the device and after it enters the device. And therefore, the unitary operator V is generated by the total Hamiltonian, the bare Hamiltonian plus the interaction term, integrated between T0 and T1. And the unmeasured work is then defined as the average change in internal energy of the system with respect to the bare Hamiltonian H before and after it undergoes the unitary evolution. So the direct TPM protocol aims to construct the statistics of work by performing ideal measurements of energy before and after the system undergoes its isolated unitary evolution. So here we have, so before the system goes into the unitary channel, it is subject to a Luther's instrument for the Hamiltonian. And again, the same Luther's instrument of the Hamiltonian after it exits the device, which, so the whole device transforms the state rho to the unnormalized state rho tilde x, where x is the sequence of energy measurement outcomes. So if we write the Hamiltonian in spectral form, where epsilon m are the distinct energy eigenvalues and pm are the spectral projections, then the Luther's instrument is defined as follows. So for any input operator, its sandwiched by the spectral projection associated with eigenvalue m, and the Luther's channel is just then the sum of the Luther's instruments for all measurement outcomes. So therefore, so again, the outcome x is defined as a sequence nn, where n is the initial measurement outcome, n is the final measurement outcome, and in the random variable of work, which is the function of x, is just the difference in energy eigenvalues, and the probability of observing sequence x given the initial state rho and the unitary operator v is just the trace of the final unnormalized output state, which is this object here. Now, with some basic algebra, then you can evaluate the average work, given the probability distribution and the work, which you can write equivalently in these two forms. So, so you can see that if you want the average work to equal the unmeasured work for all system states rho, then the Heisenberg-evolved Hamiltonian has to be a fixed point of the Luther's channel. And similarly, if you want the average work to equal the unmeasured work for all unitary processes, then the initial state rho has to be a fixed point of the Luther's channel. Now, since the fixed points of the Luther's channel are the commutant of the Hamiltonian, That is to say, an operator is a fixed point of the loose channel if and only if it commutes with the Hamiltonian, then we can see that the average work cannot equal the unmeasured work for all states rho and unitary processes v. So this is usually referred to as the TPM definition for work not satisfying the unmeasured first law, for example. Now, how do we include the description of the measurement apparatus used to perform the ideal energy measurements at initial and final times? So every measurement process can be physically modeled by a measurement scheme. So here, I'll just describe the setup for the initial measurements because the final one is basically identical. So the measurement scheme is described. So for time tj, where j equals 0, 1, is described by this tuple here. So you have a Hilbert space for a quantum probe, an initial pure state of the probe, a unitary coupling, a unitary operator which serves to couple system and probe, and a pointer observable on the probe. So the system in state rho enters this unitary channel together with the probe state. And finally, the probe is measured by a pointer observable, which we assume to be a sharp observable, as in its effects are projection operators. And since our measurement is a Lüder's instrument, then we can quite easily characterize the action of the unitary operator, which couples system and probe, as follows. So for every vector psi of the system Hilbert space, tensored with the initial set of the probe, the unitary operator maps this to this vector here, which is, so you act on psi by the spectral projections of the Hamiltonian, and this state is correlated with an eigenstate of the projection operator Zn associated with outcome n, basically for the pointer observer. So yeah, these are eigenvalue 1 eigenstates of the projection operator Zn. I'm going to not mention the J subscript here for simplicity. Now, since the unitary coupling between the system and the probe also requires mechanical manipulation by introducing a time-dependent Hamiltonian, then this process will also, in general, require work. Right? So we can define the total Hamiltonian of system and both probes for the initial and final measurements as follows. And then we introduce also measurement interaction Hamiltonians. So for example, for the initial measurements, so h int 0, it is non-vanishing only for a finite duration. So after t0 prime, which is a time before the system undergoes its unitary evolution, and then it vanishes again when the system starts going its own isolated unitary evolution. And similarly for the other interaction with the other probe. So that's non-vanishing only after the system undergoes its isolated unitary evolution, and it remains non-vanishing for a finite duration because we're assuming that the measurements don't take infinite time. And if you write the total unitary operator, given both, so it's generated by the total bare Hamiltonian of system and probes, the system only interaction Hamiltonian, which describes its isolated unitary evolution, and also the measurement interaction Hamiltonians, now integrated for this extended duration from t0 prime to t1 prime. Now with a bit of algebra, you can basically simplify this as follows. So this is the measurement unitary coupling between system and the first probe, and this is the measurement unitary coupling between the system and the second probe. This is the isolated unitary operator on the system alone, and these are unitary operators generated by the bare Hamiltonians of the two probes. So we can basically, so these θ1 and θ2 are basically the time duration when for the whole process, when the interaction Hamiltonian is 0, essentially. And so therefore, well, we can define the total unmeasured work for the whole process, which is again, so here P subscript pi 0 is basically the projection on this pure state. So this is just a compact way of writing the equation. So again, it's the increase in average energy evaluated before and after the total unitary evolution. Now, if the TPM protocol is a universal definition for work, then it stands to reason that we can also apply it to this extended unitary process, evaluated on both the system and the probes as well. And therefore, so self-consistency really means that if we perform the TPM protocol on this extended system and then ignore the apparatus degrees of freedom, or the probe degrees of freedom, in other words, then we should recover the original work distribution for the direct TPM protocol of the system alone. So you can also think of self-consistency as compatibility of the total work distribution and the system-only work distribution. So here's the schematic for the extended TPM protocol. So again, you have the measured system and the two different probes. So again, each of them is measured is subject to an ideal measurement of their bare Hamiltonians before and after the total unitary evolution. And yeah, so we have a extended sequence of measurement outcomes. So MN is again the measurement outcomes for the system of interest. And these are the sequence of outcomes for the two different probes. And so these also have a probability, which is again evaluated by looking at the trace of the final state, but we don't need to worry about the details here. And so here's the basic first result, which is quite trivial in retrospect, but so basically a sufficient condition for self-consistency, which I defined just previously, is for the probes to be initialized in a state which is an eigenstate of the respective probe Hamiltonians. And the reason is quite simple to see, basically. So if the probes are eigenstates of the Hamiltonian, then the initial energy measurements on the probes will not disturb them. So therefore, the unitary interaction between the system and the probes will cause the same state transformations that you would have given the direct TPM protocol. So that's a pretty simple result to see. But now we want to see when the unmeasured first law is basically satisfied for all system states and system-only unitary processes. So here we basically impose that the Hamiltonian of the probe is equivalent to the pointer observer, which means that if we can write the probe Hamiltonian, the bare Hamiltonian probe as follows. So we have the projection operators of the pointer observable. Each of them is associated with a energy eigenvalue. So then, therefore, when we perform the ideal measurements of the probe Hamiltonians, we're essentially performing a measurement of the pointer observable itself, right? So when we evaluate the average work for average total work for the extended TPM protocol, well, in general, we always get this equation, right? So if you remember from a previous slide, we basically applied the Lulus channel for the Hamiltonian on the input state. Now, of course, since the probe states are eigenstates of the Hamiltonian, there are fixed points of the Lulus channel on their respective Hilbert spaces, so they remain invariant. But of course, since you're performing energy measurements on the system as well, you apply the Lulus channel to the initial state rho. Okay, so that's not very surprising. But if we satisfy this condition, then this equation turns out to actually be equal to this equation, where we can kind of remove the Lulus channel acting on the system state. And this, if you recall, is just a definition of the unmeasured total work. And this equality will be satisfied for all system states rho and all system-only unitary operators V, right? Because we're only fixing the unitary interaction between system and probe and the probe, the initial states of the probe. But the initial state of the system and the system-only unitary operators can be general. So, yeah, so given this condition that we can impose on the probe Hamiltonian, we see that we can always satisfy the unmeasured first law for the total work for all system states rho and unitary operators V. And the reason for this, intuitively speaking, is that Lulus measurements are strongly repeatable. Now, recall that given the extended TPM protocol, we still perform in Luther's measurements on the system initially as well, right? But strong repeatability essentially means that if you perform a Luther's measurement, an ideal measurement, and you perform the same measurement again, you basically don't get any state changes after the first measurement, essentially. And given that the structure of the unitary operator V, the total unitary operator, and the fact that our energy measurement on the probe is a measurement of the pointer observable, which induces a Luther's measurement of the system, we can see that the direct measurement of energy on the system becomes superfluous. So we can kind of ignore, like remove the direct measurements of energy in the system, and we still get the same statistics for the work. So that's the intuitive physical picture to see this peculiar result. Now, so when is the total work distribution identical to the system work distribution? So we have the total work distribution, so it's just given by this equation here. So it's the delta function. So it basically captures the probability of there should be an X. So you just look at the probability of sequences X, and you sum them up for all sequences where the work equals W, right? And the system-only work distribution is again given by this equation. Now, these two equations will be identical for all system states rho and unitary operators V, if and only if the unitary interaction between system and probe does not has a zero unmeasured work for all system states. So we can write this as follows. So again, the Heisenberg evolved Hamiltonian of the system and probe J minus the bare Hamiltonian. So this evaluated given the initial state of system and probe is zero for all system states. And this condition is also equivalent to the statement that the probe or the subspace of the probe that is involved during the measurement process corresponding to a single degenerate subspace of the probe Hamiltonian. Now, of course, we can also say that the probe Hamiltonian being fully degenerate is sufficient, but for technical reasons that I won't get into here, it's not necessary. So you can still have a non-degenerate probe Hamiltonian, but only a single degenerate subspace is involved during the measurement process. And also in relation, so the equivalent statement of the unmeasured work being zero for all system state rho. So this is in a sufficient condition is again for these unitary operators to commute with the Hamiltonian, but again, it's not necessary. You can find simple counterexamples where this equality is always satisfied for all system state rho without the unitary operator U commuting with the Hamiltonian. So just to conclude, the TPM protocol is self-consistent definition for work if the total work distribution for the compound of system plus apparatus is compatible with the system-only work distribution, which is to say that when you ignore the apparatus degrees of freedom, you recover the work distribution for the system alone, given the direct TPM protocol. And such self-consistency is satisfied if the apparatus probe states are energy eigenstates. Now, I didn't show that this is necessary, but I would be surprised if it wasn't. But showing necessity is just needs more tedious calculations. And also, if the apparatus Hamiltonian is equivalent to the pointer observable, then the total TPM work distribution will satisfy the unmeasured first law for all system-only states and system-only unitary processes. And finally, the total work distribution will be identical to the system-only work distribution for all system states and system-only unitary processes, if and only if the probe Hamiltonians are effectively degenerate, which is equivalent to the statement that the unmeasured work due to the system probe coupling vanishes for all system states. And that is all. Thank you.